Okay, so why do we care about this so-called E number? Okay, so we're reaching the point 2.718282473. Let's talk about why that number is important. So suppose you could compound interest continuously, that is, over smaller and smaller periods of time. Like I said in the previous video, we could do milliseconds or nanoseconds, for instance. The sequences of value for the total gets closer and closer to the number E, which is approximately equal to 2.71828, etc., etc. Like pi, the number E can be found on your calculator. What does our calculator display for E? So E is a little bit trickier to use on our calculator, so let's go ahead and see if we can find it here. E, now you can't just use the green E's here because it's not quite the same one. See how we had pi here, and if we just hit pi, we'd have to do second, of course, pi, and then hit enter. It gave us what it could give us, 3.141592654, etc., etc. Same for E. Now E, though, is going to be, you're going to have to hit your second key again, and then if you go straight down to this ln key, it says e to the x power right above it. You're going to see what ln stands for. Don't call it ln. It's actually natural log, which we'll learn about here in a moment. But e, you always take it to a power. So if you just want regular e, you're going to have to take it to the first power. So you put in a 1, close your parentheses, and you have e to the first power, which is your regular e. So your value that your calculator gives is 2. Oh boy, here we go. So 2.718281828. Now it looks like there's a lot of 2's and 8's and whatnots giving us a pattern, but it actually doesn't. It does not give us a pattern, so don't let that fool you here. Okay, so just like pi, it's an irrational number, and it could be found on our calculator. Now this number is going to keep going, again with no pattern, and this number is actually named after somebody very special who was the discoverer of it, you could call it, and his name was Euler. And you might be thinking that does not spell Euler, but that's his funny pronunciation. So if you want to spell it out phonetically, it'd be like Euler, okay? Not Euler, not Bueller, it's Euler, okay? So Euler was the dude, and he was really cool. He had one of those fancy hairdos way back when, and he kind of came upon this number here, and this is why we call it E, I think. I don't know, I made that up, but I think that's why they use E for it, to stand for Euler. Alright, so number E is named after Euler, who proved that the sequence of numbers of the form 1 plus 1 over n to the nth power approaches a particular number as n increases. That number is, and here's E for you, to about a bazillion places. So like I said, I know there's a lot of 8's and 2's at the beginning, but it actually does not have a pattern if you look at it here. This is all about sequences and series, which you might learn about in pre-calc next year. So just know that this is maybe like the first one that you ever saw here. Okay. So notice like pi E is also irrational, meaning it doesn't terminate, doesn't repeat. It goes on forever and ever. Okay. So let's say we were lucky enough, and I have yet to come across these in one of my day, but who knows? They might be out there. We were lucky enough to come upon a bank who compounds things continuously, meaning not even by the second, like every snapshot of a second. Okay, so all the time it's being compounded, your interest here. So we have what we call a continuously compounded interest formula, and it's much like the other. It says if an amount P is invested in an account paying an annual interest rate R of compounded continuously, the amount A in the account after T years will be excuse me, A equals PE to the RT power. I call this the PERT formula, you know, like PERT Plus, the shampoo. That's how I remember it. It's the PERT formula. So the A, the P, the R, and the T all stand for what they used to. So let's go ahead and label them here. Please make sure you do. So the A is the amount after a certain time, so amount after time. P is your principal. E is Euler's number, so that one we don't really have to mark. It's your 2.71828 number. R is our rate again, so that's our rate. We don't need to worry about how many times we're compounding it. That's what the E takes care of. So there's no N's here. So, and T is time in years again. Okay. So go ahead and make sure you have all those written down. You should typically have this whole slide written down, so please make sure that you do. If you need to pause, please do so. Okay, so let's see how we use this PERT formula. So I'm going to just go ahead and write it. Well, let's write it down here because we are going to use it. So A equals PE to the RT power. R and T are exponents here. So it says if $850 is invested at an annual interest rate, rate of 6% compounded continuously, what is the amount in the account after 10 years? So again, we kind of have the same setup as we did with our old interest formulas. We have $850, which is the principal, so that's going to be P. Our rate is 6%, so that's R, and 10 years equals the time we're going to be put in here. So we don't know how much we're going to have left. We do know our principal is 850. E is just E. And then to the RT, now remember we had to convert this into a decimal, so it'd be 0.06. We always go 2 places from where it was. Okay, so 0.06. So that goes up here, 0.06 times T, which is 10. Okay, so then we go grab our calculators. Please get yours out. And we have 0. Oh, let's turn it on here. So we'll clear it out. So 0, well I guess we would put the E in here, and this whole thing would be my power, and it's nice enough it puts parentheses in there for us, so that'll be taken care of. So we have E, so it's second and then your natural log button, so E, then 0.06 times 10, and then close your parentheses, and then we need to multiply that by our principal, which is 850, and we get our answer here. Alright, so A equals, oops, 15. Yikes, hang on. I was thinking 8. I had 8 on the brain. Sorry, so it's $1,548.80. Okay, so quite a bit of money. We almost doubled what we put in only 10 years, so that's quite a bit. Right? Now, if you wanted to, you could compare that to just compounding it annually. So that formula, remember, was A equals P times 1 plus R to the T power. Let's plug everything in here and see what we get, just for argument's sake. So our principal was 850, and then 1 plus, our rate is 0.06 to the T power, and T, remember, was 10. So let's go ahead and put that in there. So 1 plus 0.06. Sorry, forgot my decimal point. 0.06, and we take that to the 10th power, and we multiply that by 850, and we get an amount of $1,522.22. So now this is not our answer, nor did they even ask us to do this, but I just wanted you to realize that, hey, if I compound it continuously, I will get $548, or $1,548 versus $1,522. And well, you know, that's what, 26 bucks? 26 bucks might not seem like a lot, but let's say you didn't start out with 850. Let's say you had $1 million in there, and that would end up being a huge difference. So if you can compound it continuously, if you can find a bank that does this for you, that would be the best situation you could find yourself in. Okay, it will always win out every single time. Okay, so we have one last example here. It says the amount L of a certain radioactive substance remaining after T years decreases according to the formula L equals B to the negative 0.0001 T power. So if we have a different formula here that we've got going on, that doesn't mean E is any different. E is still the number 2.718, etc., etc. Okay, so it's the same E, just a different formula. So if 2,000 micrograms, that's a mu, that's a Greek symbol, it's called micrograms, are left after 6,000 years, how many micrograms were present initially? Okay, so they tell you the amount is left after 6,000 years. So the amount L of a certain radioactive substance remaining, so that's what's remaining, so we know that our 2,000 micrograms is what's remaining, so that's going to be L. After T years, well, it's been 6,000 years, so that is going to be T. Okay? And then we got to figure out, I guess, what B is here. So we have L equals B times E to the negative 0.0001 T power. And, okay, so let's start plugging in here. So we have 2,000 in for L equals B times E to the negative 0.0001 times T, which is 6,000. Okay, let's start simplifying. We can clean up this exponent here. So 2,000 equals B times E to the, well, I gotta figure out what that is. Hang on one second. Negative 0.0001 times 6,000 here. What do we get? Negative 0.6. So negative 0.6. Okay, and then we're looking at this equation over here on the left, and again, we'd have to divide by B, get a mess of a number here. I'm not going to do that. This is one of those cases, again, we don't know how to solve for this yet. We have yet to learn about logarithms, so we're going to save that. We're going to split this up in two, and we're going to have one y equals here, and another y equals here, and we're going to go to our calculator and see if it can help us. So let's graph these two equations. So I have my old ones left in there from the last time we did this. Whoops. Okay, first one I'm going to put in is this. Now typically, now be aware, these are not two different variables. Remember, E is our number down here. So I'm just going to change this to an x, because you don't want to put b in there. It'll mess with our calculator. You always put x in there. So let's put in x times e, so then we put our e down here, to the negative 0.6 power. Ugh, I think my calculator needs to be recalibrated. Okay, 0. There we go. Alright, so that's our first equation. And then our second equation, we're going to go ahead and put in y equals 2,000, because that's where we want it to be. Okay, then we go to our graph, see if we get a nice picture. Whoops, sorry, I went to my table, hit the graph. Let's go back to our standard window so we can see what we're working with. So zoom 6, no good, all I see is my line here, so we want to go ahead and zoom out. And zoom out again, because I'm only getting one line here. Let's zoom out again, see if we have any luck this time. Let's zoom out again. Any luck? Aha, we're getting somewhere, but we can't see their intersection point. So let's zoom out one more time. Aha, there we go. Now it looks like what we have is two lines crossing here. Remember, we care about where they cross each other, because where they cross is where this line is going to equal 2,000, which is exactly what we want. We set them equal to each other over here. So how do we find their intersection point? Remember, go back to your calc menu, so second calc, down to intersection, which is the fifth option, and check your first curve, make sure you're on that line. I'm good, so I hit enter. Second curve, am I on that line? Yep, hit enter again. One more time for it to guess, and boom, we have our intersection. We know y is going to be 2,000. What we care about here is x, which is 3,644.24, we'll say. Okay, and that's all the information we needed out of here, so let's get rid of that. So how many micrograms were present initially? Well, we would have 300, let's clean this up a little bit, 3,644.24 micrograms, okay, initially. Okay, which makes sense, because we're decreasing, so if we have 2,000 left, we should have expected that we would have started out with something higher than that, which would be 36,000. Or 3,600, sorry. Okay, so that answer does make sense, so we're good to go. And that's all we have for continuous growth or decay. So again, this is building upon our exponential growth and decay here. We're just using that very special number E. See you tomorrow.